what I want to do next is introduce, excuse me, introduce our first keynote, and that is from Necmiye Ozay, who's an associate professor of electrical engineering and computer science at the University of Michigan. Necmiye is received her PhD at Northeastern, a master's at Penn State, and she's part of the controls group at the Robotic Controls Group, as well as part of the Robotics Institute. She also is affiliated with the Institute for Data Science at the university and the Institute for Computational Discovery and Engineering. Necmiye is also a career CPS award winner from, I don't know when, probably 2013, 2014. She was one of the, I think the second, probably the second group of CPS career awards that we made. She's done really well, gotten many subsequent grants. The good thing about her work is it really bridges both the engineering side, the controls side, and the size directorate side. So it kind of really in one person, you have this person who, a researcher, who really has a perspective on computation and the information, as well as a deep understanding of controls. So she is going to talk about formal methods for cyber-physical systems. She's going to help tell us what the state of the art is and future challenges. So please give a hand to Necmiye, who
Okay, thanks, David, for the introduction. It's my pleasure to be here talking to you today. Today, I will try to give you an overview of formal methods applied to cyber-physical systems and several advances that we made in this area in the last decade. And I will try to mention what are some remaining challenges. Maybe it's a bit redundant for this audience, but cyber-physical systems are all around us, from self-driving cars, surgical robotics, infrastructure systems, and agricultural systems. And the questions that we try to answer is, can we give end-to-end guarantees on safety and test completion? Can we somehow go beyond safety and also guarantee requirement satisfaction? And how do we do that? And the type of tools that we are developing in this domain is called formal methods. So this is a definition from Wikipedia. They are mathematically rigorous techniques for specification, verification, design of software and hardware systems. And I will try to give you some examples of formal methods being developed within this community, and what are some advantages and disadvantages in using those type of methods. So the first method maybe in formal methods is verification. And in verification, you start with a system model together with the software that controls this system. This is your autonomy software over here. So you have this closed loop system. You know both your hardware and software. And you have your specification. And you try to develop this algorithmic box that checks whether this dynamical system, when you close the loop around it with the software satisfies the specification. And as a result, you can get two different things. You can get a correctness proof or correctness certificate, or you can get a counterexample that shows you that there's a bug in the system and you cannot, this system is not guaranteed to satisfy the specification. So this is great because if you can do this, you get strong guarantees, but hybrid system verification is computationally very hard. It's typically undecidable. On top of that, this computational hardness gets even worse due to this autonomy software part, because most of the complexity in many problems, it's not coming from the physics, but it's coming from the software side. So there are millions of lines of code. Here are some examples. For example, if you go to the Mars Curiosity rover, it has 5 million lines of code. If you go to an average modern high-end car, it has 100 million lines of code. And the software part is hard to model and hard to scale due to its complexity. And our community has been working on trying to get abstract models for this decision-making module so that we can apply our verification tools. But we have been also thinking about alternatives to this paradigm to get around this complexity induced by software. And one alternative is correct by construction control synthesis. And that's an area that I work on. And in this case, what you change is that, okay, if the software is what is making my problem hard, let me start without the software. Let me just start with my plant model and specification, and let me ask the question, does there exist a software module that I can sort of close the loop around my system with, such that when I close the loop around my system with the software module, the closed loop system satisfies the specification. And again, we are developing these algorithmic tools in the synthesis box. And the output of that thing is either a software module with correctness guarantees, together with a validity domain that tells you under what conditions or which parts of your state space this module is guaranteed to satisfy or guaranteed to enforce your specification. Or you get a proof of impossibility that says there exists no software or no decision-making module that can satisfy this specification. Then you can go back to your system and maybe you improve your sensor, you improve your actuators, or you go back to your specification and you relax your specification because your physics is not capable of satisfying what you want to do. Again, this has some advantages and disadvantages. If you can do this, you get strong guarantees. It avoids the complexity induced by the software part, or maybe it doesn't avoid, it just pushes it elsewhere. Instead of working with the software, you are just trying to produce it. And it explains fundamental limits. It gives you an idea about impossibility. So that's also a nice feature. But on the other hand, there are also disadvantages. Correct by construction synthesis is computationally even harder. So you are trying to solve a harder problem. Verification is just a special case. We can do this only for limited type of specifications. And correctness of your specification becomes more crucial. And completeness of your specification becomes more crucial because typically you cannot synthesize a decision-making module partially with knowing partial specifications. And if you come up with new specifications, you cannot incrementally do that, although we have work in the community trying to do that. You typically need to redo. And there's almost no synthesis approach to work with learning and perception modules. So we can verify those things, but maybe we cannot synthesize a computer vision module. So I will give some examples from my own group's work with collaborations with others in the synthesis domain before telling you about other alternatives. So we have worked on many applications and we developed new tools for the synthesis box. I won't tell you what specific tools that we developed, but I try to focus on the applications. And we have worked on many applications, mostly in automotive and aerospace domains. and I will give you two early highlights on adaptive cruise control and lane keeping. This was about like 8 years ago when I was starting my career. These systems were not as standard as they are now in most of the vehicles. They were just like rolling out. And we started to look at these systems, and we wanted to see whether we can automatically synthesize this software that auto companies are trying to develop using engineers. And it turns out we were successful in doing that. We developed new synthesis tools. We synthesized controllers, and we deployed them in MCD, University of Michigan's test facility. So here are some examples from the deployments. This is MCD, if you are not familiar with it. It's 2-3 city blocks with autonomous vehicles that we can use to test our ideas. We also have a digital twin of MCD, and we can synthesize software. We can put this software on the digital twin, and we can run the exact same software on the car. So this is a small, short video, but the thing is, this is the software running on this car is not written by a person, it's written by another algorithm. We just input the system model, we input the specification, algorithm spits out the decision-making module together with the code running on the vehicle, and we can just put it on the vehicle. So what did we learn from these early deployments? So there are a few maybe things that we learned that motivated future research. Putting correct and automatically synthesized software on a car is feasible. We have run many experiments, and actually this was part of Jesse Grizzle's Frontier project with Paolo and Aaron. So we collaborated on these things, and we were convinced that we can put automatically synthesized software on vehicles. There were failures. They are correct by construction, but correct maybe in quotations. But having mathematical models and formal assumptions help to detect these failures. For example, when we start looking into failure cases, since we already synthesized using a formal method, formal model, we quickly realized that our model was missing actuator delays. And there are actuator delays from the steering wheel and actual rotation of the wheels of the vehicle. And this wasn't modeled in our model. And at runtime, you can use your model to monitor what's happening. And if you see a failure, you can correlate and figure out what the reason for that failure is. Another thing we realized is the safety envelopes and controllers that we were synthesizing were maybe a little bit conservative. And one reason for conservativeness is we were using state feedback type control structures, and these are not looking ahead. So you can think about these controllers as digging a hole at the bottom of your vehicle and looking down and trying to drive just by looking down. But we as humans, we always look ahead. We have predictions of the future, and our initial attempts didn't take that into account. That motivated some new research. For example, another thing I forgot to mention, the models that we have, they work on certain operating conditions, but if we want to deploy the vehicle in different weather conditions, our models change a little bit, and we weren't initially able to adapt to those changes. But then we extend our tools to take into account learned models and learn models on the fly and resynthesize. We develop techniques that take into account these delays as part of the future work or current work, and we have some results on how predictions affect your safety margins. And there's a poster about that in the afternoon session if you are interested about it. And the thing that we could do is we could take this points that we learned from experiments, and we can go to theoretical results from them, and we can get theorems from experiments as well. For example, if you're a control person, when you see delays, you will be scared, because if you have a dynamical system and if you start having delays, you are essentially making your system dimension blow up. And as I said, scalability and computational issues in these domains are important. You don't want to deal with a large dimensional system. So this was initially scary because our methods maybe don't scale well. And one thing, for example, taking this thing that we learned from the experiment, we can develop new theory where we showed that if you have an n-dimensional linear system with k steps of actuation delay, your overall system dimension ends up being n plus k. And if you have lots of delay, then your synthesis algorithms are maybe exponential in this n plus k. We showed that there exists an auxiliary system that's still n-dimensional, such that any safe or invariant set of this n-dimensional system can be transformed into an invariant or safe set of your actual delayed system. Essentially, by using the structure in the dynamics, we show that although these delays, they increase your system dimension, they don't really increase your complexity. So this was kind of a nice learning loop, deploying things, looking at the issues, and coming back and developing new theory. Okay. So let me go forward. I said correct by construction control synthesis is one alternative to verification. Another alternative is falsification. And in falsification, now you say, I don't need a plant model. I don't need a model of this software. And I can handle arbitrary complexity. So everything is black box to me. I will have still my specification, and using this specification, I will try to find counterexamples and bugs. And the outcome is either a counterexample or it's inconclusive. So the disadvantage here is that the advantage here is that although you can handle arbitrarily complex models, including learning components and everything, you get weaker conclusions. But I think this is one of the success stories of our community. Now there are falsification tools adopted by industry. I don't know if Sanjit is here. I saw Shriram here. He is one of the developers of Estaliro. Georgios is also one of the developers of Estaliro. And these are tools now industry use regularly. But there are also disadvantages, as I said. This is not as strong of a guarantee, so this cannot prove correctness. Also, this typically doesn't give you an explanation of the counterexamples. So it can give counterexamples that are trivial in the sense that you don't get a sense of whether that's a bug in your software part or that's a limitation of your hardware. So motivated by this, and also using our experience in synthesis, we came up with a slightly different paradigm that we call synthesis-guided falsification, where we say, okay, we are pretty good at modeling vehicles or certain physical systems, not all, but certain physical systems we are pretty good at modeling. So if I have the model of the physics, but my software can be complex and still black box, can I do something smarter and do this falsification faster? And can I come up with counterexamples together with explanations of counterexamples in the sense that, is it a bug in the software that's fixable versus is it a limitation of the physics itself? Again, the key idea here is falsification is, in a sense, random search, smart random search. And if you have your plant model, you can steer the search more efficiently. You use not only your specifications to steer the search, you can use backward reachable sets of this plant model also to steer the search and make the search space smaller. And then you query this black box software only at specification critical parts that are also critical for your dynamic. And we took this and applied it in using real software. So I don't know if you are familiar with Comma AI. It's a self-driving company. And they have a GitHub repository. You can download their software. So we just downloaded their software. It's a big black box for us. We put our falsification, synthesis-guided falsification tool around it. And we found some counterexamples. Actually, their adaptive cruise control was pretty good. We couldn't find anything that made their adaptive cruise control crash. It was very conservative. But what you see here is that there's an internal safety margin that they set. That's this red line over here. Their adaptive cruise control was violating that internal safety margin that they themselves set, but it wasn't crashing, so it was pretty good. For lane keeping, we could generate scenarios where it's possible to steer your vehicle properly, but this algorithm was not able to steer the vehicle properly. Actually, it took us a year to integrate this software box with our tools. And in the meantime, they upgraded. They were using a PID-based controller internally. They upgraded to an MPC. So by the time we published the paper, the software that they were using was different. Nevertheless, 2 days after I put the paper on archive, I received an email from the CTO of the company. And we had an interesting conversation afterwards. And we have some small extensions to this. This is kind of ongoing work. You can do this for vision-based controllers as well. So here I have a vision-based controller in simulation that does pretty well in most of the cases. If you just randomly simulate this thing, it will go around this truck in front of it. But with our falsification tool, we can figure out scenarios where if we manipulate the video a little bit, that's maybe not visible in a way that's not visible to humans, we can make the same software crash. And again, this is using similar backward reachability type ideas. Okay, so this was kind of an overview of formal methods in CPS. I talked about verification, synthesis, falsification, synthesis-guided falsification. And I told you, depending on what you know about your plant or what you know about your software, you can use different things. They have advantages and disadvantages. But there's an elephant in the room that I didn't talk about. In all of these, you need a specification. And how critical is this specification? And for the rest of the talk, I will try to get a little technical and talk about the specification part a bit carefully. And let me go back to the cruise control example. So if you want to apply these things, you need a mathematical model of your system. And if you are, for example, in a mechanical engineering department, you can take a whole graduate course on how to model a vehicle. But I don't think there's any course on how to write formal specifications, because if you want to formally prove something, you need formal specifications as well. And when we were doing adaptive cruise control, maybe Paolo would remember this. Our first attempt was, oh, let's write a specification, adaptive cruise control. It's easy. We wrote, if there is no car in front, go at a set speed given by the user. If there's a car in front, follow the lead car. Would this work? Then you stop. But it's close. It's close. Pardon me? Getting close. So that we also had a region, the radar limit. The thing that this was missing when we synthesized first that we realized, you are going at a set speed, a lead car comes in, you start following the lead car starts speeding up. They exceed the speed limit, and you exceed the speed limit as well. They get a ticket, you get a ticket. So it turns out that it's not that trivial to write specifications. So you can write something and it might look correct, and you synthesize something, it's correct with respect to this specification, but maybe your specification is not good enough. Then Paolo led this effort, and he went and found the standards from ISO and SAE. We studied the standards, we compared them, and we wrote our final specification. And it's pretty complicated. And the question is there an easier way of coming up with specifications? So it shouldn't be 2-3 people with PhDs, multiple smart grad students trying to figure out what the specification is. And especially if we want to deploy these type of tools in small businesses, in smaller manufacturing settings, where the end users might want to update things frequently, and they might not have the skills to write specifications. And that's the thing that I am going to talk about for the rest of this talk. Maybe I will get a little technical here as well. And the idea is, as I said, we spend lots of time with modeling. We have courses about modeling, and we also know how to go from data to models. So we have system identification tools, learning tools for models. But we can also use data maybe to learn specifications. And if we can learn such specifications, we can take our specification, and if we know the system model, we can use them in synthesis, correct by construction control synthesis. We can use the specification to monitor our system at runtime, and we can do anomaly detection. But there is one thing that's kind of different in some of the CPS domains that I am interested in. That's different than typical machine learning approaches. We are typically in a small data regime. And the reason is the following. Think about the following scenario. You have a small manufacturing business. You are trying to use automation to assemble certain specialized components. And every now and then, the component that you are assembling changes. Now, do you want this small business to find 100 workers to demonstrate the task so that their automation system can learn the specification and do the task? It defeats the purpose of automation if you really need lots of data for every small update that you might need. And I will focus on this small data regime, but again, the idea here is that if we can do that, if we can learn from demonstrations with small data, then we can use our synthesis methods, and we can also generalize in the sense that we can perform the same task in new environments. For example, your manufacturing business, one day you are using a robot arm, then you upgrade your robot arm. You don't need to relearn everything. As long as you have a model for your new robot arm, you already learned the task of assembling this component, and you can use synthesis to get your manufacturing line working with the new robot you have. Okay. So is this a new idea? Not really. There are similar things out there, and it's called learning from demonstration. And again, as I said, specifying tasks and requirements by hand is challenging, and people were aware of this for long. And the goal in learning from demonstration is, given demonstrations of a task, you try to learn a policy which completes the task in similar scenarios. And the common approach here is inverse optimal control. So this goes back to Corman. But there are also like newer incarnations of this for different problem classes, like inverse reinforcement learning. Here, what we assume is that the demonstrator solves an unconstrained optimization problem. So they try to minimize a cost function. And you try to define some features and write your cost function in terms of a linear combination of these features. And the goal is to infer this cost function, or infer this gamma. And once you learn this cost function, you can do your planning with the learned cost function. And this has been successfully demonstrated. This is from early 2000s. Peter Abiel did inverse reinforcement learning. And you can do some amazing things with this idea. Of course, if you want to ensure safety, there are certain things missing here. And those are the things that we try to address here. So what if my task involves constraints? What if there are unknown constraints? If you want to do an IOC type approach, then you put your constraints into your cost function with a soft penalty. Then you may not really satisfy the constraint when generating new trajectories because it's kind of softened. And depending on the criticality of your constraint, this might be a good idea or not good idea. You need these cost features. It might be as difficult to write these cost features as writing your entire cost function itself. And it's difficult to scale this multi-stage tasks. For example, if you have a task where a barista robot is filling a cup of coffee, grasping the cup, delivering the coffee without a spill, you need like 3 different cost functions at different times, and it's hard to write down cost functions for these type of tasks. So what our approach does is we try to directly learn hard constraints, and I will start with static constraints, and I will show how it generalizes to more dynamic multi-stage tasks. So here is what we assume the demonstrator solves, and we get trajectories that are solutions of this problem. These are trajectories psi. There is a safe set parameterized by some theta, and this is unknown to us. We are the learner. The safe set is unknown to us. And maybe there are some known constraints that we have access to as well. For example, maybe we know the dynamics of the robot that does the manufacturing business is using. Or maybe we have the start and end positions that are required. And here is an example. Maybe this is a robot carrying a heavy object over glassware, and it's trying to avoid this region above the glassware. And there's this hard constraint. You don't want to get in there. And that's the thing that we want to learn, but maybe we know the initial and goal positions of this object that we are trying to carry. Our problem, the learner's problem, is given some demonstrations, we want to find a constraint parameter that makes these trajectory demonstrations that are given to us optimal. And the core challenge here is that we need to be able to distinguish between valid and invalid behavior using only valid behaviors. We don't want to like crash our vehicle or crash our broke our glassware to give demonstrations that are invalid. So it's kind of learning only with positive examples. And the other thing is that we want to be doing this in a sample efficient way. So how do we do that? If we can assume demonstrator is optimal and in our, or at least locally optimal, it turns out to be a very strong prior. And you can use that to write down a reasonable learning problem in terms of an optimization problem. And essentially, we are using ideas similar to optimal control. We are using Crash-Kantaker optimality conditions to write a problem in the dual domain to search for these valid constraint parameters. And what are KKT conditions? There's primal, let me go back. There is primal feasibility. So if these are the two demonstrations that I have, I want to eliminate this as a constraint set because my demonstration goes through the unsafe set. So primal feasibility eliminates these type of constraints. Then you have stationarity and dual feasibility and complementary selectness that essentially ensures local optimality. These are constraints based on dual variables that ensures that if you move your trajectories, perturb your trajectories a little bit, you start being suboptimal. And this can dramatically reduce the set of valid constraints. Using this local optimality dramatically reduces the valid constraints, and you can do things with much less number of trajectories or much less number of demonstrations. So this is the type of problem that we need to solve, and we showed for certain types of constraint parameterizations, this ends up being a mixed integer linear program, even though your dynamics are nonlinear. This integer constraints come from complementary selectness, how we encode that. There is one issue, though. This is typically ill-posed because this doesn't have a unique solution. So you come up with valid constraints, but for each valid constraint parameter, you have a different constraint set. And here is an example. All these ellipsoids are valid constraints. If I have only one trajectory, my constraint set can be any of these. But it turns out that you can use this technique as a constraint checker. That's something you can use in like motion planning type algorithms. And the way to do that is the following. If you query a point, you can just write the problem and you say this query point is unsafe. And if you do this, and if this problem turns out to be infeasible, then this query point is guaranteed to be safe. And essentially what's happening here is that you have this feasible set in your parameter domain and dual variable domain. And this is essentially something like a projection, a little more than a projection of that thing where you are intersecting all possible constraint sets. And that intersection of all possible constraint sets give you a guaranteed unsafe domain. And you can also find a guaranteed safe domain, and there will be some uncertainty left in between. So here are some simulation results. We can learn these constraints, and we can plan with them using our synthesis algorithms. We can do things with quadrotors. But what happens in multi-stage tests? So the difficulty here is now we have time-varying constraints that must be satisfied. We want to learn these constraints from safe, locally optimal demonstrations. And again, we want to be able to synthesize controllers that we can deploy in new environments, guaranteeing safety. So what is different here? First, we need a hybrid constraint description because there are continuous things happening in my state space and there are discrete things happening due to these different stages of my task. And for that, we use linear temporal logic. You can use signal temporal logic as well to describe this discrete part. And we will try to learn this temporal logic specifications from optimal trajectory. Many of you might be familiar with temporal logics, but they have a grammar. For example, you can represent things like A happens until A must hold until B holds. Something must always hold. Something should eventually hold. So this is kind of safety type tasks. This is kind of reachability type tasks. And these are things you can represent with temporal logic. then you need to connect these discrete actions to the continuous world, and you do it using atomic propositions. And these are capturing the geometry of being in certain regions of the state space. So how do we now encode a similar problem in this multi-stage task domain? We will have these atomic propositions. These are low-level continuous constraints, and we will have a parameterization for that. And we will have this structure parameters at the high level describing your discrete constraints. So here is the task of fill the glass, grasp the glass, deliver. So the first one is saying, don't visit P3, don't go to the delivery lot before you go to the place where you will grasp the cup. Then don't grasp the cup before filling it in, and eventually deliver the cup. So you can write a complicated specification of this one. Of course, we want to learn this structure without having the structure. And the way we do it is to search over these syntax trees that are generating from the grammar of the logic. And this is a discrete structure. Again, this is mixed integer linear representable. In the end, we can write our problem as learning the structure parameter that's discrete, learning the continuous parameter that captures the geometry, discrete parameter that captures the grammar, and it's going to be a very similar problem. So the core idea, we can use KKT for enforcing continuous optimality, but the discrete part, optimality really doesn't, at least KKD really doesn't give you any extra information, because locally every discrete decision is optimal, because these are discrete decisions. If you perturb, you go to continuous domain, and it's infeasible all of a sudden. And to enforce that, we need a notion of discrete optimality. And why discrete optimality is important? If you think about logic, there are trivial specifications that are satisfied with the same trajectory. For example, this trajectory that fills the cup, delivers the cup, it satisfies the trivial logic formula that's true. Or another trivial logic formula that says, oh, just go to the end position. So from a logical correctness point of view, there is no difference between this and this if your formula is eventually reaching the goal. So there are demonstrations that all your demonstrations are feasible for far weaker formula structure. This is harder to enforce, and essentially this boils down to enumerating lower cost solutions, but you can use the fact that if you are deviating from a trivially lower cost solution, it should be because you need it for your discrete structure. And we utilize that in a counterexample guided falsification loop to learn these discrete structures together with the continuous structures. And we can give some theoretical guarantees on consistency, probabilistic correctness, probabilistic completeness, guaranteeing that you are returning the simplest possible formula in the grammar, and it's conservative in the sense that safety-related continuous domain propositions, you learn inner approximations of those. And here are some examples on this barista task and on this quadrotor task. And we also did some experiments with a real robot. So we used a VR environment to give demonstrations, and it's a complicated task where you need to grasp the soup, place in a small box, deliver it to the blue region. Let me maybe play, oops, let me play. So this is a demonstration that's given in a VR environment. It's a multi-stage task. It's a robot delivering different items to different people. And we learn the formula structure. In this case, we sense the AP, so we are not doing continuous learning. And here is planning with that formula structure in a new domain where you are doing the same task, but the objects are in different positions. And you just use your synthesis engine to come up with a new plan, and your robot goes and implements that in the new domain. Okay, so maybe wrapping up slowly, synthesis or formal verification, and most of the formal methods in general, they require both models and specifications. We are very good at teaching how to do modeling. Maybe we are not giving that much emphasis on teaching how to specifying things. And both modeling and specifying your requirements can be hard. And learning can help in both aspects. And if you have this small data regime, if you are in the small data regime, optimality is a very strong prior that can be utilized. And it helps a lot in your sample efficiency. And we have some current work in learning probabilistic constraints for safety of very large-scale complex systems, and we have a poster about that as well. So let me step back a little bit. So these are the repertoire of tools that this community developed over years, but there are still things that are missing. And let me mention those a little bit. We can use these tools to increase the trustworthiness of CPS systems. Maybe we can decrease the time to deployment from design to deployment, but there are some challenges. Scalability, there's lots of great work in the community for scaling things up, but still more complex, more high-dimensional, more nonlinear learning-based components, they are challenging. And scalability, not in the model sense, scalability in the specification sense is also challenging. As your specification gets more and more complex, your scalability drops. Learning is another thing, another elephant in the room. We can learn things, but how do we trust these learned artifacts? How do we trust the data sets that we learn from? Formal methods for human cyber-physical systems. Humans are hard to model. Humans are hard to specify. So there are lots of challenges there. And maybe another frontier is formal methods for multi-agent CPS with multiple decision makers, including humans, that maybe takes into account all of these challenges because you need to scale, you need to analyze this multiple decision-making entities, and it's even very hard to safely evaluate without deploying, and these are some of the challenges that we have. And I will end with some acknowledgements. This is, of course, done with a huge team of students, graduate and undergraduate. This learning specification work was mostly Glenn's work, who just graduated with his PhD, and he's doing a postdoc right now. The other students contributed to safety of driving applications work. There are undergrads here. Sunho is a new grad student working. He's talking in he has a poster here talking about learning probabilistic constraints for complex systems. I had the fortune of having lots of CPS collaborators. Most of them are here. I would like to thank to them as well. I would like to thank funding agencies. And lastly, I would like to take this opportunity to thank Kishan Baheti, who was the program manager of my NSF CPS, NSF Career Award that was jointly awarded between CPS and EPCN programs. And with that, thank you so much.
Do we have any questions?
Well, I'll scream. Thank you for letting me talk. One question as a non-expert in this is, we've led a lot of kinds of failure modes for autonomous vehicles. Get stuck in situations that just weren't anticipated, or something which I didn't quite hear is where the information that gets gathered by the sensors is obviously wrong, as in it reads a speed limit sign as 10 miles an hour, but a human would know that that's just, I mean, the sticker on the speed limit sign, it really says 50. So you correctly do that, but come on, how do you deal with these type of erroneous sensor input or just unanticipated situations that you just can't specify, but every human would know? And how do you find out that these exist, which ones you don't handle when you don't know that they don't exist? Kind of the unknown unknowns in that sense.
So that's a very good question. Unknown unknowns are hard. One of the things, but there's also effort in the community regarding that. So one of the things, for example, you can use falsification type approaches. Let me go back to my slide there. Although this is kind of work in progress, there are people, okay, you don't see my slides anymore. I was trying to, can we, okay. For example, these type of approaches can try to figure out deficiencies in the sensing and perception part. But this is still not unknown unknowns, because I am assuming I have a simulated environment, and the type of inaccuracies that I can experience in real life exist in the simulator, and in that case I can search for them. But other than that, unknown unknowns, I think it's pretty hard, and I don't have a good answer to that.
Okay, thank you.
Sure.
Hi, Necmiye, thanks for the great talk. I was wondering if you could comment on two things from the learning from demonstrations approach. First being, at what scale does the description length of the constraint that you're learning become kind of intractable or reach sort of the infeasible space? And the second thing is, when you reach, or when you're dealing with concept classes of specifications that are no longer things that could potentially be encoded in mixed integer linear programs, how does the generality of this learning from demonstrations approach still apply to those sorts of more complex concept classes?
Those are both very good questions. The thing is, MILP solvers are pretty good, but also the type of specifications, okay, we can do this like multi-stage task. I don't know if your task has like 6 stages, then you need to search this big tree, and the number of discrete variables are exponential in the depth of the tree, so things get a little hard. One of the things that we are looking at right now is that there is lots of work in constraint solving and MILP communities to come up with problem-specific branch and bound heuristics. And that's something we are exploring, because these problems have structure, and we are using off-the-shelf MILP solvers. If we can come up with faster ways of solving specific type of mixed integer programs that appear in these type of problems, that might be a way. But that's the answer that I have at this point. And the second question was the concept class. So if you trust nonlinear solvers, by all means, you can use them. But I don't have a like, we are essentially looking into optimization community and what they have and trying to exploit it as much as possible.
Thank you.
Yeah, thanks for a great talk. I had a question about the formal specifications, comments about formal specifications you gave at close to the beginning of your talk when we were looking at the adaptive cruise control. On the one hand, you pointed out the difficulty in writing down formal specifications. On the other hand, people who are writing down informal specifications face the same difficulty, I guess. And so I guess my question is, how much of the difficulty is due to maybe the unfamiliarity of the formal notations, and how much of it is just inherent in the complexity of the problem?
I think both. I think like capturing human intent, although we are like very good at communicating in some sense, we are not also too good at communicating our intent. And that comes up in specifications and requirements. But I still think that trying to, and one maybe a bit of a high level, formal methods won't solve all your problems, but they can sort of restrict the search space, restrict the things that you should look at, restrict the type of simulations you should run to get more confidence in your system. You can also, like, given the synthesized artifacts, you can still simulate and show the human and get feedback. But I totally agree. We are like, it's not only ability to write formal specifications, it's in general ability to express what you want. That's a very good point.
Thank you.
Hi, Necmiye. Thank you for a nice talk. I had a quick question. It seems like the examples that you used throughout the talk were examples where it's not unreasonable that when you actually implement control, you can pretty much measure the whole state of a system or the whole state of the plant. But I can think of a lot of examples where this might be useful, but where you maybe have very sparse sensing in your plant, so you have an additional layer of uncertainty. So I'm curious if that poses problems in the applications of these techniques. For example, where the specifications that you have concern variables you cannot measure directly.
Of course. So if you have any decision-making problem and if you have partial observation, that adds to your complexity. And most of the times you lose your ability to get complete answers in the sense that you cannot characterize all the initial conditions or all the conditions that your controller is guaranteed to achieve a task. But you can abstract out these estimation modules with some error bounds, and you can do something a little conservative. There is work in the literature, including my own work, how you work with estimators in the loop. And the problem is slightly easier if your specification is on the observables. Still hard, but slightly easier if the specification is on the observables. It's much harder if the specification is on the unobservables. Then you can go to things like epistemic logics, because like knowing what's happening is part of that thing, and there are logics that has a knowledge operator. That's something we looked briefly recently, but complexity gets a bit too much in that case.
Yeah, I'd like to follow up on the example for the cruise control. So obviously, if you write specs wrong, then the system isn't going to work. You'll match the specs, but the system isn't handling it. So in cruise control, imagine that you also have to worry about when there's fog, when it's raining, when it's snowing, when someone cuts in front of you, you're in a construction zone. You know, so there's many, many real-world issues that have to be addressed. And so if you design an adaptive controller that is very simple, and the spec's very simple, and then you put it out there and it doesn't handle any of these conditions. So how do you add all of those kinds of constraints, known constraints, into your specs?
Actually, I have an anecdote about like exactly what you were asking. We were talking to a car company when we were developing these specifications, and they said, oh, our spec is so complicated. We have this like 21 different conditions, company unnamed. And we asked, what are those conditions? A car can cut in, and that cutting in car might be slower. A car can cut in, and that cutting in car might be faster. A car can get out, and now you have a new lead car. And they are like enumerating all possibilities and writing the requirements for all these possibilities. What we did instead, in our model, we have a hybrid system with a reset map that captures the behavior of lead car. Then your specification becomes very simple, and you capture all the 21 different cases that they want to capture. So there is this complexity in between the model and the specification. It's not really two separate problems. You can embed some of your complexity in smart modeling. And since we had experience, like we are working in hybrid systems, it was very natural for us to have that cutting in, cutting out behavior, model it as a hybrid system.
Okay.
And we had a very simple hybrid system with 2 modes. Very simple compared to their specification, a very simple specification that handles their like 21 different requirements. So
Okay.
there's like, if you are good at modeling, that helps. I think that's
Okay.
kind of.
Yeah, that's very interesting, and I think that, to me, because I'm not really a formal methods person, would give me insight that, you know, a higher level abstract kind of spec could actually incorporate all of these real world considerations. And highlighting that, for, especially for CPS people, would be really helpful, I think. But thank you.
Thanks.
Yeah.
Yeah. Thanks so much for this talk. And I wonder that if you have any comments on using the feasibility of using some soft constraints or soft properties, soft specifications instead of those hard constraints, because hard constraints can usually be really computationally expensive to be working with. And there exist some soft constraints such as temporal robustness scores for signal temporal logics. So I wonder if you have any comments on that. Thank you.
So that's a very good question as well. I think it's, again, part of specifying. So your specification doesn't need to be a hard constraint. It could be, you can have a probabilistic specification. You can think about softening that specification. I would say it depends on the problem, right? If there's a cliff and if your car is going through the cliff, there's no soft constraint there. You will fall off the cliff. But maybe if there's a soft thing that you can go and crash instead of like going out, like jumping out of the cliff, then you can, so it's, I think it's related to how you specify, and it's very problem domain specific. And there's definitely value in soft constraints. And one of the things, for example, we looked into is in these constraint satisfaction problems, we looked into things like, can I parameterize my constraints in a way that when I learn the safety domains, those domains are also parameterized. And you can look at sensitivity of the type of things that you are computing to different specifications, and that's kind of a soft specification. Then you can see, okay, I can soften this constraint because you are making the bound of the constraint a parameter, and you are synthesizing using that parameter. So that's one way that we handled that, but I think that's a great point. It's specification engineering, and it's important.
Yeah. Thanks so much.
Okay, so want to give a round of applause for Necmiye.